so now for 39, it's kind of a similar situation. It says to get off a frozen, frictionless lake, which is a fancy way of saying we're not gonna count friction, right? To get off a 65 kilogram person, takes off a shoe. Doesn't look like a shoe, but that's the best I could do. And it says that the shoe weighs 0.150 kilograms. And it throws the shoe horizontally, directly away from the shore. So, like, we'll call this the shore. I threw it that way, and this is the shore. So, this is like a frozen lake or something, right? And this is the shore. So, this is like land. Okay? Throws it away from the shore, and it has a speed of 2 meters per second. So, the shoe, which is here, has a velocity or speed of 2 meters per second. Okay? And that's an initial velocity. Well, it's also a final velocity. Actually, it's not an initial velocity. We'll talk about that in a second. Let's just say the speed. I'm just going to write it down for now. That's a funny looking shoe. Okay? Oh, and one other thing. They said that the person, the distance from the shore to the person is 5 meters. And it says, how long does it take to reach the shore? So let me read this one more time, all the way through without drawing the picture. It says, to get off a frozen frictionless lake. That's why he threw the shoe. He was on a frozen lake. If there's no friction, it's frictionless. You can move all day. You can't move, right? Oh, there is an answer. So to get off of the frozen lake, he knew, he must have been a physicist, if he threw his shoe, that when he threw his shoe this way, he would drift the other way, and that's what he was trying to do. So to get off the frozen frictionless lake, a 65 kilogram person takes off a 0.15 kilogram shoe and throws it horizontally directly away from the shore with a speed of 2 meters per second. If the person is 5 meters from the shore, how long does he take to reach the shore? So his thinking is, if I throw this shoe this way, right, throw this shoe this way, I'll move this way. Does that make sense? Well, when it says how long, so we've gone through, we've listed, we've read it, we've drawn the picture, we've listed what we know. Is there anything else that we know? That's pretty much it, right? What do we need to know?
How long?
How long? What are they referring to?
Time.
Time. So somewhere, we need to figure out what the time is. All right. So now we're going to need some equations. Well, I'm going to list this a little different. So what do we have? We need to find time. We have a distance, we'll call that delta x, of 5 meters. I can't remember what the sig fig was. I think it was 2 or 3. We have a person that has a mass, so we have a mass of the person, which is 65 kilograms. We have the mass of the shoe, which is 0.150 kilograms. Maybe it is 3. Is there anything else that I'm missing? Oh, the velocity. We have the velocity of the shoe, which is, was that the initial velocity or the final velocity? That's the final velocity of the shoe. So that was 2 meters. Is everybody okay with us going to the right as being positive? All right, so we're going to label this so we know right off the bat. That's positive, that's negative. Okay? So, I guess we're not quite done though. Is that all we know? Is there anything else we know? See, I thought we listed everything, but you know what? If that's the final velocity of the shoe, what was the initial velocity of the shoe? 0. So the initial velocity of the shoe is 0. Well, if I have the mass of the person and we have a velocity of the person, what is the initial velocity of the person? 0. So what's the final velocity of the person? Wait, it says that he has to move. He has to move to the shore. What is his final velocity going to be? It's going to be negative, that's true, but do we know a number? Huh? And we need to find it. So technically, not only do we need to know the time, maybe we need to figure out his final velocity. Okay? Now here's another thing I know. I also know that delta x is equal to a velocity times time. And here I don't know his velocity, right? Because the velocity of whom? The person. And his final velocity. But I do know delta x. Alright, so what do you guys think we need to do? You guys have all this written down because I'm going to go to another slide. What else are we going to do? Well, we've listed a lot of information. So let's try to solve this thing. This section's on momentum. What do we know about momentum?
Mass equals velocity.
Okay.
Well, no, mass times velocity.
Mass times velocity is momentum, but this is really conservation of momentum. So what do we know? Yeah, so our initial momentum should equal our final momentum, right? And if that is the case, our initial momentum is equal to what? Of the system, right? So I'm gonna, this is my equal sign, all right? And so this is our like initial stuff. And this is my final stuff. In fact, let's write it in a different color so we know what we're doing here. So this is our final stuff. All right. Now this is from the other screen. You can see it on your paper, and I have it written down in my notes. So we're going to do, and then we were told that momentum is equal to mass times velocity, right? So we're going to do the person. So I say the mass of the person times the velocity of the person, initial, plus the mass of the shoe, initial. Well, the mass of the shoe doesn't change, but the mass of the shoe times the velocity of the shoe, the initial, should equal the mass of the person times the velocity of the person, their final velocity, plus the mass of the shoe times the velocity of the shoe final, right? Now in your textbook, they don't write F for final. Mr. Adams does that because it just helps me keep track. But the initial is the not, right? 0 sub 0. So that's where we start. Okay? Is everybody writing this down? Yeah? So now if everybody's writing this down, what is the mass of the person? Can somebody tell me? 65 kilograms. And we should probably, I double check this, but I should remind you guys, what is the unit of momentum? It's kilogram meters per second. And all the information they gave us was kilograms meters per second. So we didn't have to do any conversions, but I should probably mention that, okay? So I have 65 kilograms. And then what was the velocity of the person? Oh, that was easy. And what's the mass of the shoe? 0.15, right? Kilograms. And what was the mass of the shoe? 0? Oh, that was easy. Oh, wasn't my plan to write this in black? Here, we'll do this. So what's the mass of the person again?
65.
Yeah, it didn't change, right? That was a joke. Ha ha ha. Very funny, Mr. Adams. All right. So then we have his velocity. Do we know what that is? Nope. All right. So then we're going to add the mass of the shoe again, which is 0.50 kilograms, times what was the final velocity of the shoe? 2 meters per second. Right? Well, so far so good. What is the total momentum? The initial total momentum? 0, right? Because this is 0 and this is 0, so we get 0 plus 0, so we have 0 equals. All right, get out your calculators. What's 65 kilograms times the velocity? Still the same. So it's 65 kilograms, velocity of the person, final, plus, now what is this though? 0.15 times 2. At 0.3? Is it? Let me check my notes. Do it on your calculator. Is it? So now this is 0.3 kilogram meters per second. Right? Now, probably what we want to do is solve for this velocity, right? How do I do that? What's the next step? Yes?
Subtract 0.3 kilograms.
Yes. Subtract this stuff, right? From both sides. Okay. Now what do I do? Divide by 65. So now I gotta take the units with it, right? So I'm gonna say 65 kilograms. And then over here I'm gonna divide by 65 kilograms. Now, when I have a kilogram in the top, I have a kilogram on the bottom, they cancel. With regard to the meters per second, well, let's say it this way. What is 0.3 divided by 65? 0.3 divided by 65.
0.0046 random numbers.
Okay, so it's a bunch of numbers, right? So it's probably something like, let me see, I have it in my notes here. Is it -4? Well, it's probably a bunch of zeros, but if you put it in scientific notation, it would be like this. Times 10 to the -3 meters per second. Now, depending on how you have your calculator set, it might be like -0.004. Is that what you guys have on some of your calculators? Is that what you had? How many zeros from the decimal? 2, right? And then like 615 meters per second. Now, Mr. Adams wrote it in scientific notation because it's a little easier for me. But what's the difference between the two? Yeah, where the -3 comes from is that I had to go this way 1, 2, 3 decimals. Does that make sense? Is everybody with me? All right. So wait. We're done, right? That's the velocity of the guy, right? Is that the velocity of him? We're done with the problem?
No.
No, we're not. How come?
Time.
Yeah, because originally they wanted a time. What did I say we could? What was it? I said that. Because we were given a delta x, and Mr. Adams was just thinking out loud that if I took a velocity of the person times time, that equation is true, right? Now let's think about the velocity. He's on a frictionless surface. Now there's a force that's applied, sort of, right? Because remember we said the force that's applied is delta P over delta T. But once he lets go of the shoes, in other words, his body's accelerated once he lets go of the shoe because momentum is conserved. But is there anything else acting on his body in the horizontal direction once he starts moving? No, it's frictionless.
Air friction.
Yeah, air friction, but that's so small we'll ignore it. You're true. That's right. You're right. And that's true, but we'll just ignore it. Is there anything else? Is he pulling on a rope? Is something pushing him? So once he's in motion, he will remain in motion unless something else acts upon him. So what that means is once he starts at velocity, he's in motion. So his velocity doesn't change. It might change a little bit because of air friction and some other things. So I can feel very confident using this. All right. So what did we say delta x was? How far away from the shore is he?
5 meters.
5 meters. All right. That sounds good. 5 meters. And his velocity was negative 4.65. That's ugly. 615 times 10 to the negative 3, right? Meters per second. Times t. All this stuff times this. So now what? We're looking for t, right? What do I do? Divide by all this stuff, right? So if I'm going to divide by negative 4.615 times 10 to the negative 3, and that's meters per second. Whatever I do on one side, I got to do on the other. And I'm going to show you how to do this on your calculator in just a second. Now, what do we do when we divide by a fraction? Don't we multiply by the reciprocal? So when I divide by meters per second, what am I really doing? I'm multiplying by second meters, right? So could I do this? Thanks, bud. Could I do something like that? Yeah? So if that's the case, what happens to my meters? They cancel. So I get something in seconds. Well, that's good because we're solving for time, right? Now, this might be hard to do. Okay? So now, let's pull up our calculator and we'll see. It's not hard, but it's easy to make a mistake. All right. So let's clear that out. Man, that looks crazy. All right, so we had 5 divided by. Now, this scientific notation, your calculator does it a little different. They use a double E to represent times 10 raised to a power. And so on your calculator, when we say divided by, we can put it in parentheses and we say negative 4.615. Now you can manually put in 10, times 10 raised to the negative 3, and that would work. But your calculator, if you look real close, right above the comma, there's like a double E. Do you guys see that?
Yeah.
So if I hit second and then the comma, I get this little double E thing. And that's just a shortcut that says times 10 to the. Now whatever I put in here is the power that we raised 10. And what was it? Negative 3. So I'm going to hit negative sign, not the minus sign. Negative 3. Okay? Now hit enter. Whoa. Better double check my answer. That's negative 1800 something, something, something. Wait. Why is it negative? He's going backwards, but it's time. Time doesn't go backwards. By the way, the numbers are right. We just gotta address this whole negative thing. So let's come back to that in a second. Well, I know that this negative thing's right because he's going in the negative direction. What about delta x? And we kind of made a mistake. Mr. Adams, he was so excited, and I thought I wasn't going to make a mistake this problem. But if my direction going to the left is negative, if this going to the left is negative, technically he's moving 5 meters in which direction? In the negative direction. So his displacement is technically not 5, but -5. So let's make a little adjustment for that. So if I come down here, technically I should put a -5 right there, right guys? And if I do that, what does that make my answer? Positive, because the negatives would cancel. So I've got a positive 1,083, and we'll just approximate there. Oh, it's seconds, right? Right? That's a lot of seconds. Does it say how they wanted us to do it? Can we figure that out in minutes? How would we figure that out in minutes? I'd say 1,083 seconds times 1 minute is equal to what? 60 seconds. You guys remember when we learned how to do that at the beginning of the year? This cancels with this, so what do? I'm going to take this number and I'm going to divide it by 60. I got 18.5, but if I round off, I've got 18.1 minutes. Don't worry about the negative sign. So T is that, or 18.1 minutes. What did the back of the book say? Seconds or minutes? Minutes? Okay. That's still a long time, right? Any questions though? Do you guys know how to do this? Does it make sense to you guys? Yeah?